Dear student, welcome to this fourth lecture on the optimal control, and we continue the lecture from the previous lecture. So, in the previous lecture we have considered the problem of finding the optimal control for the equation 1, that is dx by dt is a function of x of t, u of t, t. X is the state variable and u is the control variable, and the performance index to be minimized is the function j given by s of x capital T comma t plus integral t0 to capital T and capital F of x t u t t dt for suitable functions s, f and small f, etc. So, now we define the Hamiltonian in the previous lecture we have already defined. So, we just recall the result. H is equal to capital F plus lambda dashed into small f, where lambda is the vector lambda 1, lambda 2, lambda n. So, and lambda transpose is the row vector and f is the column vector given in the equation 1. Then the Euler-Lagrange equation to be solved for finding optimal control is given by this equations 3, 4, 5 and 6, where 6 is the boundary conditions. Now, we have seen one case in the last lecture, that is if the end point, if the initial point is fixed and final point is also fixed. So, if we consider t0 and capital T, and at t0 the value is x of t0 and at capital T the value is x of capital T. So, we consider functions of this type for the optimal state. So, x of t is the state variable, initial condition x of t0 and final condition x of capital T, both of them are fixed. T0 and T capital T are also fixed values. So, in that case we have the del t, there is no variation in capital T because it is fixed. So, that is 0, and there is no variation in the value of the final position, that is del x of x t, that is also fixed here. So, is 0. So, the condition 6 will not appear directly, all the 4 conditions are given, all the 2 conditions are there. We have to solve the system 3, 4, 5 subject to the given condition. That was what we have seen in the last lecture. Now, we will see the other cases. So, for example, consider the problem x1 dot is x2, x2 dot equal to minus x1 plus u, sorry, this is u. U of t, and initial condition x1 of 0 is 1 and x2 of 0 is 0. This is fixed and the final time is a variable and final position is fixed here. X1 of capital T is 0, x2 of capital T is 0. So, this is the case in which T0 is fixed and the initial condition is fixed here, and at final time T is a variable, but this is fixed, that is the value is fixed. For example, it may be a curve of this type. So, capital T is not fixed, it can be any of these values. So, here we are drawing just for one dimensional problem. For example, if you take this as x2 of t, at t equal to capital T the value is 1, and for any capital T the value is 1. So, we can get many such functions. Out of these functions we have to find the optimal function. Similar graphs can be drawn for x1 of t separately. So, how to find the control u of t, optimal control for this particular problem? For doing that, we proceed using this 4 equations 3, 4, 5 subject to the boundary condition. Now, if you observe the boundary condition, the final position is fixed, therefore, del x t is, there is no variation in the final position. So, this is 0, but del capital T is arbitrary, there is a variation. So, the boundary condition is h plus del s by del t at capital T should be equal to 0. So, that is the boundary condition, other conditions are given here. So, we have to solve the equation del h by del u equal to 0 is one equation, and del h by del x equal to minus lambda dot d lambda by dt, and the other equation is del h by del lambda equal to x dot. So, that turns out to be the given equation itself, and the boundary condition is h plus del s by del t evaluated at the final position is 0, okay, where capital T is also to be found out, unknown function. So, first del h, we will first write the h value from the given problem. The Hamiltonian is given by the capital F x2 square plus u square by 2, that is capital F, plus lambda 1 lambda 2 that is the row vector, multiplied by small f is the function x1 dot equal to x2, that is the first value, and x2 dot is minus x1 plus u. So, this is the h function, which is equal to x2 square plus u square by 2 plus lambda 1 x2 minus lambda 2 x1 plus lambda 2 u. So, this is the h function. Now, del h by del u, if we calculate from here, it is equal to u of t, and here del h by del u is plus lambda 2. So, it is minus lambda 2. Del h by del u is u plus lambda 2 equal to 0. So, therefore, u equal to lambda minus lambda 2, and del h by del x. So, it means del h by del x1 first. Del h by del x1 is minus lambda 2. That is equal to lambda 1 dot, the first one. The second variable is del h by del x2 is 2x2 and plus lambda 1 so that is equal to lambda 2 dot from this equation. So, this implies these two equations, and del h by del lambda, if you see, that is nothing but the function x itself, it is x2 and minus x1 plus u, that is the left hand side, equal to x1 dot x2 dot, that is from the third equation. This equation implies this one. Now, h at capital T, if you substitute capital T at for all this thing, so this implies x2 square at capital T plus u square at capital T by 2 plus lambda 1 at t x2 at t minus lambda 2 at t and x1 at t plus lambda 2 at t and u at t. So, that is equal to 0. Now, we substitute from this equation u is equal to, let us say it is 1, u equal to minus lambda 2, we substitute it in this equation. So, x2 square plus u is c equal to lambda 2 minus lambda 2. So, it will be lambda 2 square by 2 here plus lambda 1 into x 2 at capital T minus lambda 2 at t and x 1 at t. Here again u of t is minus lambda 2, if you substitute it is minus lambda 2 square equal to 0. So, here we have lambda 2 square by 2 etc. So, the condition is this is at t, everywhere we do not write capital T. So, we can write like this. So, we have x 2 square plus lambda 1 x 2 minus lambda 2 x 1 and this 2 combined we get lambda 2 square by 2 equal to 0 at t equal to capital. So, this is the condition on capital T. Okay. So, first thing is we have to solve this 4 equation, coupled equation. So, this equation and we have to solve the equation lambda, the first we will write this one x 1 dot equal to x 2 and x 2 dot equal to minus x 1 plus u, u is equal to minus lambda 2. So, we substitute this u is minus lambda 2 and then lambda 1 dot equal to minus lambda 2 and lambda 2 dot is 2 x 2 plus lambda 1. So, it is the coupled equation that is to be solved. So, we can solve it like the usual dynamical system problem. It is like x dot is equal to capital A into x, where A is a matrix whose coefficients are given in the right hand side, and we can find the solution with these conditions. So, we have the condition, initial condition already given in the here x 1 0 equal to 1, x 2 0 equal to 0. So, we have this condition also. So, after solving this we will get 4 constants C 1, C 2, C 3, C 4. To find the 4 constant we have to make use of this condition as well as the boundary condition given in this expression. By substituting in this expression we can solve the problem for the 4 constants. After finding the value of say lambda 2, we substitute in the equation 1 and that gives the control function u of t, that is the optimal control, and the solution x 1 and x 2 obtained from here is called the optimal state variable for the given problem 1 here. Okay. So, now we will consider the example 2. Here in this example we have the simple example x dot 1 variable problem. So, here x dot is equal to 2x plus u and initial condition is fixed. The initial time is 0 and initial position is 1, that is fixed. We have to minimize the functional j which is given in this expression. And here we have this capital T, final time is free as well as the final position is also free. So, we have, it is a one variable problem. So, T is a independent variable and x is the dependent variable. X of 0 equal to 1, at t equal to 0 it is 1, and capital T is not fixed, it can be anything, and final time is also anything. So, the optimal control problem is it can be any of these curves, and because final time, final position, both of them can be arbitrary here, but it should minimize the functional j. So, to solve this problem we make use of the usual equations 3, 4, 5 subject to the boundary condition here 6. So, we see here h, so this expression. So, here the initial time is fixed and the final time is arbitrary. Similarly, initial position is fixed and final position is arbitrary. So, now we will make use of the equations 3, 4, 5 subject to the boundary condition 6. So, let us see, because final time is free. So, del t is free, del t is arbitrary. Similarly, final position is also free. So, del x suffix t is also arbitrary. So, it is these are the two arbitrary functions del t and del x t. So, that implies that these two brackets are to be 0 separately, that is h plus del s by del t at capital T should be 0 and del s by del x minus lambda at capital T should be 0. So, these are the boundary condition, other conditions are the same in both the problems. So, let us write this equations. So, h is equal to x square plus u square plus lambda times the right hand side 2x plus u. So, we will write here in this problem the h function is x square plus u square plus lambda times 2x plus u, and the conditions are del h by del u equal to 0. So, that implies 2u plus lambda equal to 0. So, that implies u is equal to minus lambda by 2, that is one equation. The second equation is del h by del x equal to minus lambda dashed. So, that implies lambda dot. So, lambda dot is minus del h by del x. If you differentiate h with respect to x, it is minus 2x and plus 2 lambda. So, that is lambda dot equal to minus del h by this, and already the problem given is x dot is equal to 2x plus u, where u is minus lambda by 2. So, minus lambda by 2, and the boundary conditions are, so these are the two coupled equation. So, boundary condition or the first boundary is x of 0 equal to 1, that is given. Other conditions are h plus del s by del t at capital T equal to 0 and del s by del x minus lambda at capital T, because both capital T and the final position both are free, these two should be equal to 0. Now, we can evaluate, S is given in the problem, that is x square of capital T is the function s of capital T. So, here s of x of t comma t, that is given by x square of capital T. So, del s by del t is 0 because s is not a explicit function of t. Okay. So, del s by del t equal to 0, but del s by del x equal to 2x, because s function s is nothing but x square function. If you differentiate, it is 2x here, and we have to evaluate all this at capital T. So, when we substitute this thing, so this implies x square at capital T plus u square, means it is lambda square by 4 plus lambda into 2x plus u is again minus lambda by 2, that is equal to x square plus 2 lambda x, and here lambda square by 4 and lambda square by 2. So, we will get minus lambda square by 4. So, that is equal to 0. This is at capital T. This wherever the small t should be replaced by capital T, that is 0. So, this equation gives the coupled equation with these boundary conditions. We have to solve. So, we get this expression, we can write x dot lambda dot, that is equal to 2 and minus 1 by 2, and lambda dot is minus 2x and minus 2 lambda. So, this is the coupled equation with the condition x of 0 equal to 1 and this condition x square t plus 2 lambda t x of t minus lambda square t by 4 equal to 0. So, this to be solved. So, first we solve x and lambda. So, we will get two constants C1 and C2, and using x of 0 equal to 1, we can find a relation between C1 and C2. So, C2 can be written in terms of C1. Then substituting in this expression the values of x and lambda at capital T, we will get a equation in capital T, nonlinear equation in capital T, and we can find the roots of that nonlinear equation in capital T. So, that values will give the final position or the optimal position for the optimal final position, final time capital T, and which can be substituted, and we can find the optimal control and optimal state of the system. So, this is for both final time is free and final position is free. Okay. Now, we consider a similar problem, x dot equal to 2x plus u, and initial position is fixed. So, here this is function of t at t equal to 0, x of this is 1, and final position, final time is free, t is free, and x of t is also free, but it is a little bit depending on capital T. So, if you write this equation, x is equal to t square, this is the x axis, this is t axis. So, x is equal to t square curve is like this. So, the final position x of capital T should lie on this curve. So, it is not like the previous one, it can be arbitrary. it is arbitrary, but it should lie on this curve. The end point should be any of this on this particular curve. So, x of capital T equal to t square is given. So, again we can make use of these same equations. First 3, 4, 5 equations are the same, we can make use, and in the sixth equation, the boundary condition, delta t is free. So, delta t is a arbitrary variation, and del x t is not arbitrary, but it depends on delta t, because we have x suffix t, it is t square, this term. In that particular problem, the final position is depending on the final time. So, it like the square of the final time. So, if you calculate the variation del x suffix t, it is the derivative of this, it is 2t into del capital T. So, we have to substitute in the place of del x suffix t, we will substitute this. So, this will also be in terms of del capital T. We can combine this equation. So, finally, what we will get is the following. So, here also h function is x square plus u square, that is one thing, plus lambda times two x plus u, and the boundary conditions are h plus del s by del t at capital T into del t plus del s by del x minus lambda evaluated at t, and the variation of the final position x suffix t. So, this should be equal to 0, but given that x suffix t or x of capital T, that is t square. So, the variation in the final position is the derivative into the variation into t. So, this we have to substitute here. If you call this equation as 1 and this equation as 2 and this as 3. So, substituting 3 in 2, we get h plus del s by del t evaluated at capital T plus del s by del x minus lambda evaluated at capital T. Here del x t is 2t. So, we have to multiply here 2t. So, whole multiplied by del t can be taken out. Now, this is arbitrary, del t, the variation in final time is arbitrary, therefore, this has to be equal to 0. So, that implies so, this is equal to 0, and we have the initial condition. So, the equation will be the same, because the expressions are the same, whatever we derived in the last problem, the equation is the same, x dot and lambda dot is given by the dynamical system, this one, the matrix A is here. So, we can solve the equation x dot equal to A x as x of t equal to C1 e to the power lambda 1 t into x1 plus C2 e power lambda 2 t into x2, where lambda 1 lambda 2 are the eigenvalues of capital A, x1 x2 are the corresponding eigenvectors. So, the solution can be written like this, where capital X means small x and lambda. So, this lambda 1 lambda 2 are eigenvalues, they are constants, but here lambda t means it is the Lagrange multiplier, that is totally different thing. Okay. There is no connection between this lambda 1 lambda 2 and this lambda. And so, the solution can be written like this. So, from this expression capital X of t, we can find small x of t and lambda t separately in terms of C1 and C2. Then substitute the condition x of 0 equal to 1, we will get one relation between C1 and C2. And the remaining relation we have to find from here, because we know all this expression h is given and s function is x square t, that is also given. So, s of t is given as x square t. So, del s by del t equal to 0 and del s by del x is 2x, and evaluated at capital T is 2x of capital T. Okay. So, substituting these values here, we will get another relation for the final time t. So, those equation to be solved, and we can find simultaneously capital T as well as the other constant C2, substituting those equations in this one u, we have already obtained u equal to minus lambda 2. After finding lambda value, we substitute lambda 2 of t, which is the optimal control, and then we can find, we also found the x of t after finding the constants C1 and C2. Okay. So, we get the optimal control as well as the optimal state of the system. So, this covers all the cases. In the previous lecture we have seen the constant boundary condition, and in this lecture we have seen variable boundary conditions, and so this completes the procedure for finding the optimal control problems in the continuous system. So, this type of systems we call it as continuous system because the derivatives are there. In the next lecture we will consider the discrete time systems and how to find the optimal control for the discrete systems. Thank you.